In this example, we're going to develop a population model for Las Vegas, Nevada. Now, Las Vegas experienced exponential population growth, we're told, between 1960 and 2000. According to the US Census, Las Vegas's population was 64.4 thousand in 1960, and then it had increased exponentially to 478.4 thousand in the year 2000. We're going to use this data to find a model, P equal P of T, for the population of Las Vegas in thousands of people. So P, the variable P, will be defined as thousands of people, population in thousands, as a function of the number of years after July 1st, 1960. So we are measuring time from the middle of the year 1960. So we've defined our two variables, P and T. And so we're calling the model P as well. So let's go ahead and write the data in terms of our model, what we've called the model. So in 1960, the middle of the year 1960 is our zero. So P of zero, or we can write that as P sub zero, is equal to that 1960 population, which is 64.4 thousand. So there's the population in thousands. And then in 2000, we have the year 2000, and 2000 minus 1960 is 40. So P of 40, 40 years later, or we could write that as P sub 40 in that alternate notation, is equal to 478.4. We know 2 points on our exponential curve. We have the initial value, but we don't have the base of the exponential function. We don't know the growth factor. However, we can figure it out if we have internalized those ideas from the previous section. Then we can figure out here what the growth factor is. It's actually straightforward. How did I get from P0, P sub 0, to P sub 40? It must have been through a multiplier. The multiplier would be the ratio. So I'm constructing B here. The base of my exponential function is going to be the ratio of that 40-year value divided by the ratio of the initial value. That is the 40-year base. That's the base, that's the number when I multiply that number by P sub 0, I'll get the numerator P sub 40. And so that's the multiplier that takes me from P sub 0 to P sub 40. Now, that's the 40-year base, but I want the 1-year base. 1 year is a 40th of 40 years. So if I take this ratio to the 1/40th power, I've figured out a 1-year base, an annual base B is P sub 40 over P sub 0 to the 1/40th. So let's write that down. I'll actually write it down on the next slide. So let's advance. So here it is. That right there in the big parentheses is the base, the annual base. It's the 478.4 divided by 64.4 raised to the 1/40th power. That's my B value. That's taken to the t power and then multiplied by 64.4 to give me my model. This model is written in the form A times B to the t. All right? So that's one way I could write the model. Now, if using a rule of exponents, here's a rule of exponents. If I have a base, and I'll just pick a simple base, 2. If I have a base and I take that base to a power, like to the 3rd power, and then I take that result to another power. So I have an exponentiation and then another inside and then another exponentiation. But the only base involved here is base 2. how can I, one way I can do that is take 2 cubed, it's 8, and then 8 squared is 64. So that number is 64. But another way to do it is to combine the exponents first and then do the exponentiation. How many 2's are involved here? Well, 2 cubed, there are 3 2's inside, and then I'm going to have, this is the same thing as 2 cubed times 2 cubed, so there are 6 2's altogether, 6 factors of 2. So that leads me to the idea that when I have this kind of situation, I multiply the exponents. This is the same as 2 to the 3 times 2, which is 6. And that gives me the same result I got before. 2 to the 6th power is 64. So I just use that as a simple example to help me remember how to deal with these exponents right here. If I want to write this in a simplified form where I just have one exponent, I can multiply 1/40th by t to combine them. 1/40th times t is t over 40, and so this whole thing looks like that in a simpler form. And more commonly, that's an easier form, for example, to put in your calculator or to work with. So either one of these forms is okay. They're just algebraically equivalent ways of expressing the same thing. I am going to do a couple of things here before we move on. One is that I'm going to write this in yet a third way. Another thing that I can do is actually calculate this number right here. That I can calculate that annual base as I can see what it looks like as that's just a number. I can see what it looks like. 478.4 divided by 64.4. There's the initial ratio, and then I take that to the 1/4th power, 1/40th power, I mean. And so inside the large parentheses, this thing is the same thing as 64.4 times 1.0514 dot dot dot. But I'll go ahead and write what this is displaying to be 11281. There's the full precision answer given to me, and then to the t power. There's actually more decimal places, but that's what the calculator's showing me. And so this is yet a third equivalent way that I could write this model down. The advantage of this method is I can see right there the base of the exponential function as a number. I can see that it's about 5% growth. Can you see that? If I take that base and I subtract 1 and I multiply by 100 to convert it to a percent, I've calculated R. The R here is about 5.141. I'll just write 5.14% growth. So the population of Las Vegas was growing by over 5% a year during that 40-year period, which is rapid population growth. Any of these three methods, any of these three ways of writing it out are fine. If you write it out in decimal form, though, you want it to the full precision of your calculator. So let me show you another way that I could have gotten this third form, the decimal form. I can use a statistical technique. I put the two original data points into my calculator, P of 0, so input 0, and P of 40, input 40. The corresponding outputs are 64.4 and 478.4. There's the data that I was given in the appropriate form based on the way we're defining our variables. Another way of getting the model that fits these two data points is to use exponential regression. Stat, calc, and cursor down to this one, EXP REG. So I'm going to run now EXP REG, exponential regression. Now, the nice thing about any of these regressions that are included in our calculator, the user interface to run the regression, it works the same way as the linear regression that we already learned. You select exponential regression, you specify where your inputs are, L1, comma, specify where your outputs are, they're in L2, comma, and store the regression equation in y1. For you with the other interface, xlist is L1, ylist is L2, store regression equation is y1. And then you hit calculate. I hit enter to do the calculation. And there it is. Well, look at that. This tells me an exponential regression gives me an exponential curve in that standard form, a times b to the x, t for us, a times b to the t, where a is the initial value, there's the 64.4 we have right there, and b to the full precision of the calculator is 1.0514112181. It's exactly the same thing we got here, which is, as we know, that number. So any of these ways of getting that model are just fine. The nice thing about this method right here, the exponential regression method, finding an exponential fit, an exact exponential fit for those 2 points, is you can get it stored to the full precision of the calculator in y1, you're ready to calculate. And you're also ready to calculate the growth rate if you need it. You can always get that base right there. It's the b parameter of the regression by going into variables, statistics, equation, and here's all of the information about that regression equation, including b, the base of the exponential function. There it is. You can now calculate on it, like subtract 1 from the base and multiply by 100 to convert it to a percent to see the growth rate as a percent, the annual growth rate.